Now, if you talk about nuclear reaction, this one you have to look at page 5 of your notes. Now, generally speaking, when you're talking about nuclear reaction, there are 3 kinds of nuclear reaction. Either you have fission or fusion, or you have something called radioactive decay. Okay, last week we went through what is exactly fission and fusion. That's actually this one and this one here. I didn't go through with you decay. Okay, so radioactive decay is another common type of nuclear reaction. In radioactive decay, we will say that an unstable nucleus disintegrates into a more stable nucleus by spontaneous and random emission of radiation in the form of alpha particles, beta particles, and gamma ray photons. Okay, so specific to radioactive decay, this particular nuclear reaction will tend to emit for you alpha particle, your beta particle, as well as your gamma rays. Okay, radioactive decays will emit any one of these. Okay, now for all 3 of these, fission, fusion, or radioactive decay, they will eventually become more stable at the end of your reaction. Okay, so specific to radioactive decay, it will only be classified as radioactive decay if it starts emitting any one of these particles here. That's why your definition is like this. Okay, now when you go and emit the alpha particle, beta particle, and gamma ray photons, they mention that the process is spontaneous and random. What does spontaneous and random here mean? Now, in our case, when they ask you what does it mean by spontaneous process of radioactive decay, it is just simply saying that your decay is unaffected by any external factors such as temperature, pressure, or any kind of chemical catalyst. Say, for example, you want to make a particular sample decay faster. It's not as simple as you heating it up. It's not as simple as you increasing the pressure or you adding some other chemicals inside. Nothing you do to the sample will cause the decay to go faster or slower. It's unaffected by anything. That's why we call this spontaneous. Okay, it's unaffected by any external factors. Then when it comes to radioactive decay, what do we actually mean by the process being random? So in your case, random here is just simply defined as it is impossible to predict which and when an individual nucleus will decay, because each nucleus has constant probability of decay per unit time interval. Okay, so what does this actually mean is something like this. So let me just try and write out something on the screen to illustrate for you what is random. Say, for example, I have a sample of radioactive nuclei right over here. Sorry, I have a sample of radioactive nuclei right over here. I gave you maybe say 3 samples here. Each one, if you look at the first one, I can say that maybe I have 12 nuclei inside. And then I tell you now, the probability of decay for this one, the probability of decay for this sample is 0.5. So when we know that for this sample, the probability of decay is 0.5, we know that half of them will decay. So if inside this sample here, I have 12 nuclei, I know that half will decay. So I will end up with 12 of the nuclei. Sorry, I will end up with half the amount, 6 here, missing because they've decayed to something else. Okay, but you see, the thing is, how do you know it's going to be this 6 nuclei that will decay? Because there could be other variations too. So if let's just say I withdraw the sample here, it could be that maybe the nuclei decays like this, or maybe it could decay like this, isn't it? So I just do not know which of these individual nuclei will decay and when would it decay. But all I do know is that in that sample, half will usually decay. That is what we mean by random here now. We just do not know which and when a nucleus will decay. We kind of just know in a group of them how many will decay. Okay, and the reason why we cannot predict which and when an individual nucleus will decay is because each of the nucleus has a constant probability of decay. If one nucleus suddenly has a higher probability of decay, obviously that nucleus will decay first now. But the thing now is that all the nuclei inside have constant probability of decay. We just cannot predict which one will decay here. That is what random actually means. Okay. So that one should be all right, I hope. Okay, and then after that, you move on to page 7. Page 6 is something that I already discussed with you last week. Okay, so you move on to page 7. So when it comes to nuclear decay, there are a few parameters or quantities that you're always interested in order to describe the nuclear decay. Okay, now the first one would be something called decay constant lambda. Now the symbol lambda here does not refer to wavelength, it refers to decay constant. Okay, so just now as I mentioned to you, predictions cannot be made as to when an individual nuclei will decay, but we can kind of guess in a large group of the nuclei how many would decay, right? So we normally use statistical methods to predict the decay. Okay, so one quantity that we can often use is the probability of decay of an individual nucleus over a certain time interval. So suppose 1 million nuclei of a particular radioactive isotope is observed. After 1 hour, 250,000 have decayed, then the probability of decay of the individual nucleus in 1 hour is 0.25, since 25% of the nuclei have decayed. Now, from there, you define something called decay constant. Decay constant is the probability of decay of a nucleus per unit time interval. So if in my case, probability of decay, this one I just write it here in general. If I say probability of decay is number of nuclei that have decayed over the original number, it will be delta n over n. Okay. Delta n is the number of nuclei that have decayed, n is the original number. This one will just give me probability of decay. But if I want to find the probability of decay per unit time interval, it will be delta n over n divided by the time interval, which in my case is this one. So this one will thus become delta n over n delta t. This one is specifically called your decay constant. All right. So probability by themselves has no units. Okay, but then time has unit of second. So if you take probability of decay divided by time, you're going to end up with units of per unit time for decay constant. It can be per second, per minute, per hour, per day, per year. It doesn't matter which units is it. Okay, as long as it's in terms of per unit time. Okay, so like for the earlier example above here, we say that your decay constant is actually 0.25 per hour. In 1 hour, there's a chance of 25% of your nuclei decay, in other words. So the next particular quantity that you'll be interested in knowing is activity A. So average number of nuclei that has decayed in a particular time interval is another useful quantity that can be used to describe nuclear decay. In our case, we define activity as the rate at which nuclei decay. A is just delta n over delta t. You take the number of nuclei decay, divide by your time taken. Okay, so same as before, delta n has no units, delta t has unit of time. So the units of your activity would actually be measured in decays per unit time. where it can be per second, per minute, per hour, or per day. Okay. Now for activity, sometimes they may attach a special unit to it called becquerel. Now, when you have 1 becquerel, it means 1 decay per second. In other words, it has units of per second. Okay, the moment you see activity quoted in becquerels, it's already in per second. Okay. Now, there is a particular important equation that will relate to you decay constant and activity. That one is actually given by this equation. If you want to relate decay constant and activity together, you will always use this equation. A is equals to lambda n. Okay, this equation actually tells you this. The greater your decay constant, the greater your activity. And the larger your sample size, the larger your activity. Because you can see that if this one is large, obviously this one will be large. More probability of decay means higher chance of decay. So more will be decaying. And then you have larger number of nuclei. Obviously more nuclei will decay too. So activity increases. Okay. So how they got this equation is actually not within your syllabus. You just need to know that this particular equation exists and you will be using it quite a lot in your past years. Okay, so that one is okay. Then I'll move on to the next one. Okay, then after that, we have something called count rate. Okay, so what is count rate? Now, count rate is something that you measure. Okay, now to measure the radioactivity of a radioactive sample, we use a device called a Geiger-Müller tube. Sometimes they call it just GM tube. All right, so what is a GM tube? You probably would have seen it in the movies or TVs before. You know, sometimes when you look at certain TV shows or movies, when they go to some sort of nuclear site or site that has high radioactivity, they use some sort of device to measure the radioactivity at the site, right? Where you suddenly hear some sort of clicking sound, the device will emit some sort of clicking sound, tak, 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 tak. So the thing is that if you suddenly have an increase in the clicking sound, that means the radioactivity is very high. Okay, so that one is actually what you call your Geiger-Müller tube. Okay, so what a Geiger-Müller tube actually does is this. Your Geiger-Müller tube will try to capture the radioactive emission from a sample. The radioactive emission from a sample is actually in the form of alpha particles, beta particles, and gamma ray photons. So those particles, they are captured by your GM tube through your detector window. And then after that, once your device captures the alpha particles, beta particles, or gamma ray photons, it starts to emit a clicking sound. Okay, so if you suddenly hear a very high frequency of clicking sounds, meaning to say you hear a very large number of clicking per second, this one actually corresponds to more radioactive particles being detected, indicating to you that you have high activity of decay from the sample. Because you see, if you have high activity of decay, you're obviously going to emit a lot of radioactive particles, alpha particles, beta particles, and gamma ray photons per second. So if you use a Geiger-Müller tube nearby, it will capture all these particles and start to emit a clicking sound. So if you have a lot of radioactive particles, you have a high frequency of clicking, indicating high radioactivity. Okay, so that clicking sound, how many clicks you get per second, is actually known as your count rate. Okay, the number of radioactive particles detected per unit time is known as your count rate. Okay, so an example of how they go and do radioactive measurements could be something as shown below. So say for example, this is your radioactive source and your Geiger-Müller tube is this one. So the idea is that your radioactive source will emit radiation, but the radiation will be in the form of a sphere. It propagates outwards in the form of a sphere like this. Okay, like this. So you could have alpha, beta, and gamma being emitted. So if you just look at the ones that are being emitted in this direction, it's going towards your Geiger-Müller tube. Once it passes inside your Geiger-Müller tube, that's where you hear your clicking sound. Okay. So in your case, if you try to measure count rate, there's one thing that you should know. Your count rate measured will actually always be lower than the actual activity of the radioactive sample. Okay. For this radioactive sample that I have, it probably has an activity of, say, maybe 200 and 2,500 per second. When you use your Geiger-Müller tube to measure the activity, your count rate is unlikely to be the same as the actual activity. It will not be 2,500 per second. Instead, it will actually be less than 2,500 per second. Now, there's a reason why the count rate will always be different or lower than your actual activity. The first reason is because, in the first place, radiation is emitted in all directions, but your detector can really only detect in one direction. You see, just now I told you that your radiation is emitted in all possible directions in the form of a sphere, but your Geiger-Müller tube can really only detect one specific direction like this. So it doesn't capture all your radioactive particles. It doesn't measure the entire activity. Okay. And then there are also some other reasons why your actual count rate could be less. For example, your radiation could be absorbed by the air or the detector window itself before reaching the detector. So you notice that when your radiation is emitted, it has to pass through a layer of air. It could be that your radioactive particles is already absorbed by the air itself. And if, let's just say, it managed to pass through that layer of air, your Geiger-Müller tube usually has some sort of window right over here for your radioactive particles to pass through. So it could be that the window itself absorbs your radioactive particle before actually reaching the detector that is inside. Okay, so that's what this one means. And then another thing that could actually account for count rate being less than your actual activity is because the radiation may actually be absorbed within the sample itself through a process called self-absorption. So what actually happens is that your radiation is emitted, but then after that, it got absorbed back by your sample. Okay, this is what self-absorption means. And then the next one could be this. Okay, now the last two, this one, the last two doesn't really explain why your count rate would be less. It kind of is used to explain why count rate is different from activity. Okay, because when you read this 2 points later, it doesn't really tell you why your count rate is going to be less than activity. It actually explains why is it different instead. Okay, now if you look at the first point here, daughter product or sample is unstable and emits additional radiation. It means something like this. If you started off with nuclei X, this is unstable. When it goes through radioactive decay, it will decay to another element. Okay, but in the process of it decaying from X to Y, it emits radiation in the form of alpha, beta, and gamma radiation. You emit alpha, beta, and gamma radiation. So when it decays from X to Y, what if your resulting product is also unstable? So because it's also unstable, this nuclei Y will also again try to become more stable. So it will decay again to become nuclei Z, which hopefully is more stable now. But in the process of it changing from Y to Z, it emits its own set of radiation, alpha, beta, and gamma. So when you use your Geiger-Müller tube, you're really only trying to detect the radiation from X. But somehow, because your X decays to Y and Y is also unstable and emits its own radiation, you're also detecting this set also. So that could account why your count rate is actually different from the actual activity of a particular nuclei that you're testing. Okay, that's what this one means. You get multiple possible counts from each decay. All right. And last but not least, you also have something called background radiation. So your Geiger magnetic is really supposed to only detect radiation from the radioactive sample, but there are cases where there are radiation from the background. Your Geiger magnetic is also detecting radiation from the background like this. It could be that there's background radiation here, like this, and like this. So the background radiation adds up to your count rate, okay? Thereby giving you a value that's different from your activity, okay? So that's just one thing to note. All these little points here will actually be used in one of your past year questions later on, you will see. Okay, it tends to repeat itself quite a fair bit also. All right. Okay, then let me just clear off this diagram and move on to the next one. Okay, then I move on to the last part. Now, when you're talking about radioactive decay, let me just write a proper equation here. Now, when you're talking about radioactive decay, you could have element X, which is unstable. It decays into element Y, which is stable, by emitting alpha particle, beta particle, and gamma ray photons. These are what you know as your radiation. Okay. So one thing to note is this. Your X would decrease with time because X changes to Y. Over time, your X will decrease. And then Y will instead increase with time. Okay. So Y would increase with time. Okay. So what you're really interested in is the original nuclei you started off with. If you know that your nuclei will decrease with time, how does it actually decrease? How does it actually decay? So we will tell you that generally when they decay, they follow a particular pattern of curved lines called exponential decay. If, say, for example, this is a graph showing you the number of nuclei, undecayed nuclei, with respect to time, the way that your nuclei would decay could be following curves that look like this. Something like this, something like this, or something like this. Okay, there's a very specific pattern to how it decays. It follows a curve that decays like that. This is what we call exponential decay curve. Okay, so if you have different elements, they will decay by different rates, but the pattern will still be the same. Let's just say that this one is for element X, this one is for element P, this one is for element Q. All three are different radioactive elements that decay with time, but the pattern that you see would be the same. Okay, but because they are different elements in the first place, they of course decay with different rates, but the pattern will still be the same. Okay, now for something that decays like this in exponential decay pattern, there's a particular property called half-life that you're interested in. Now, half-life can be defined in either of these two ways. Either you say half-life is the average time taken for half the nuclei in the sample to decay, the time taken for it to reduce by half, or you could define it as the mean time taken for activity of a sample to decrease to half of some initial value. Okay, the idea is you want the time for the thing to decrease by half, to reduce by 50%. So if you look at a particular graph that represents exponential decay here, the y-axis here is already the number of initial nuclei. Is expressed in fraction form. Okay, this fraction is 1. It represents the original value, 100%. Okay, so it will decay with time following an exponential decay curve like this. So when you want to see half-life, it's something like this. if you started off with 1, a fraction of 1, for it to decrease by half, you will go to 0.5, right? So what is the time that it took for you to go from 1 to 0.5? That one is your half-life here. And then what if you keep on letting it decay? From 0.5, it now reduces by half again. So if by right, it should go to 0.25, right over here. So the time that it took for you to reduce by another half again will be another half-life, okay? And then from 0.25, you want it to decrease even further, it should become 0.125, which is right over here, okay? So again, this one will have another half-life, okay? So with each subsequent half-life that passes, your amount keeps reducing by half. This is what half-life actually means, okay? So that one is all right. Okay, now then after that, just now I mentioned to you specifically that when your radioactive sample decays, it follows an exponential decay curve. There are certain particular equations that you can use to represent the graph. That one is in the next page, okay? So if you had something, wait, let me just erase this. So if in general, your nuclei decay following an exponential decay curve like this, if I tell you that this is a general parameter x versus time, you can actually represent that exponential decay using this equation, where you say x is equals to x naught exponential negative lambda t, where x here could represent any particular quantity concerning radioactive decay, such as number of nuclei, activity, or count rate, okay? It can be representing any one of these, okay? As the quantities decrease exponentially with time, okay? So now, if let's just say you want to apply it specifically for number of nuclei n that remains undecayed at time t after decaying from initial nuclei number n naught is given by this, okay? This one is to represent number of nuclei. But if you want to modify it to represent count rate, as it decays exponentially, it will become this. And you can also do the same for activity. If you want it to represent activity, it will be this, okay? Notice that it really follows this general equation, just that you're replacing out the variables with what you want, okay? So one thing I should probably mention is that your lambda here is again your decay constant, your t is the time that has passed, and then your n naught or r naught or a naught or x naught is basically the initial value at time t equals to 0, okay? And from there, there's just this last part. Now, when you do your equations, when you do your calculations using these given equations here, please make sure that the units that you use for lambda t is consistent, okay? Lambda is the decay constant as before, but make sure it must be consistent with t. If let's just say for example, lambda is in per minute, t must be in minute. If lambda is in per second, t must be in second. If lambda is in terms of per year, then t must be in terms of year, okay? You don't necessarily need to use SI units, just make sure the units are consistent in the first place. The reason why you do that is because the units will cancel off. Because you see, if, for example, this one is per minute, and then you multiply with minute, the units will cancel off, right? That's the reason why we told you it doesn't really matter whether it's in SI units or not. It must be consistent so that eventually the units cancel each other off. Okay, so that's for that. Okay, then after that, we move on to the last part. Now, there's a particular derivation for nuclear physics that you need to know. You need to know how to derive this sometimes it's either half-life equals to ln 2 over lambda, or lambda equals to ln 2 over half-life. There's an equation that you will always use that relates decay constant and half-life together. That one is actually this one. Okay, so this one, the derivation is required inside your syllabus. You need to remember how to derive it. Okay, so let's just try and derive it now. Now, for example, if you're talking about a graph of number of nuclei versus time, you know it will decay exponentially like this. There's a connection between time and decay constant that's given by this equation. You learn this from above. Now, after one half-life has passed, you expect the number of undecayed atoms or nuclei to have reduced by half. If, say, for example, this one is n naught, and then after that you say one half-life has passed, n naught will subsequently reduce to n naught over 2. Okay, that's what this statement here means. So when t is equals to half-life, your n will become half of n naught. So this equation that you have will then become this. Half n naught equals to n naught exponential negative lambda half-life. So your n naughts will cancel each other off, eventually giving you half exponential lambda half-life. But the exponential function there is in the way. So what you want to do is you want to get rid of it by lning both sides of your equation, so that you get ln half equals to negative lambda half-life times ln e. But ln e itself is actually equals to 1. So now you will get negative ln 2 equals to negative lambda half-life, which eventually will give you either one of these equations. Or either you can say lambda is ln 2 over half-life, or half-life is ln 2 over lambda. Okay, so either one. Okay, depending on the context of the question. But the gist is that you need to know the derivation. All right.